It's going to be a long day for you guys, but hopefully some of you are still awake, and I can get some of your attention a few more minutes before happy hour. Right, my name is Faisal Siddiqui, and I lead ML infrastructure for recommendations at Netflix. So, by a show of hands, how many of you are Netflix members here? Okay, good, thank you. Yes, no is an acceptable answer, and I can talk to you after that. In terms of, I have a question for you guys. How much time do you think we have before to present to you specifically a good recommendation of something to watch before we lose your attention and you go away and do Facebook or something else?
30
seconds.
3 seconds.
3 seconds. Wow. It's actually it's about a minute, and so you're in the ballpark. And if in that time we are not able to recommend to you some of the best content behind this box, then essentially we've lost you. And so one of the things that my team does is try to figure out what is that perfect show for that perfect context for that perfect time that we should recommend to you and splash it up on a big billboard image the moment you log on. We use machine learning a lot in many of those aspects, and we really want to hold your attention and try to make sure that you come back and enjoy the moments of joy. So the Netflix recommendations team has a long history coming from the days of the Netflix prize back in the late 2010s, and over time, what we've seen is that the metrics that we use for essentially optimizing some of these recommendations has been evolving. Yeah, and ultimately we've boiled it down to it's the member joy that we really want to put in focus. And so our goal in the personalization space is to figure out how should we recommend content to you so we can enable the discoveries of engaging content that can essentially maximize member joy. And my talk today is going to be talking about how we in the infrastructure world help enable discoveries of such engaging content. Okay, so the outline for the talk today, I'll provide a little bit of a domain context in terms of which specific domain we work on. Then I'll spend some time going over what would hopefully will be a familiar ML infra stack. It's applied in the context of a personalization domain, but you can see parallels from what I'm talking about from Jeremy's talk about Uber earlier today. And I think Hope in this room was talking about how Intuit and QuickBooks have built their ML platform. So there's a lot of commonalities between the talks, but there are some different flavors to it. We have a slightly different opinionated view in our domain in terms of how we go about what we call the platform. So you'll learn a little bit about that. And then I'll spend some time going and doing a little bit of a deeper dive into two major subcomponents of that particular platform. Okay, so for everything is essentially a recommendation. If you look at the current Netflix homepage, there are various aspects that we can personalize, starting with which particular rows we need to show. There's a candidate of thousands of different types of rows because you watched something, we're going to recommend you something. Shows with a strong female lead, you want to continue watching something, your my list, and there's literally thousands of different row candidates, and we have to pick just a handful of them. And not only do we pick them, we have to make sure that they are in the most appropriate sorted order, because even if we send, let's say, 40 rows to your display port, you're not going to be seeing all of them. So that's one problem. Every title that appears here is essentially ranked by relevance to you. So the ones on the left-hand side are more relevant to you. Although, as we've gone more global and international, we have languages which consider this side as more relevant, and so that has to adapt appropriately. And then each of the images and the artwork that shows up is also personalized for each account member profile, which is to say that you may get a different Stranger Things image than I would. And it really depends upon your preferences, your viewing history, the context that you're coming from, the time of day even. And so essentially this aspect of trying to present essentially what is a list of stuff to watch on Netflix has tons of different machine learning use cases embedded into one homepage that we serve to you. Let me talk a little bit about the context, sort of the systems context around which some of this becomes a reality. So we have a lot of streaming data from members who have been enjoying content on our service. So we essentially start with data from millions of users. And that feeds into the various model training pipelines. And again, for each of these different use cases that I talked about, there are different types of models, there are different pipelines. And at any one point in time, we're running various A/B tests, which means that are 5 or 10 or 20 different cells for each A/B test. So there's literally hundreds, even thousands of training pipelines that we are feeding off of. Eventually, we come up with various models for each of those pipelines. Once we have those models trained, we essentially feed this into our Precompute system. Much of our work in the recommendation space does not need online training. So most of our context is around training large models that happen in an offline context, and then we are essentially able to provide a model for scoring. Even the scoring system, we have had a lot of wins by being able to go to a pre-compute batch approach, which is to say that every so often, few hours, we would pre-compute a ton of data. Essentially, we would re-rank the entire Netflix catalog for every member profile multiple times a day. We pre-compute all of this and cache it, and then it really becomes a serving issue of caching it at low latency, high throughput. So that's what we do in the pre-compute system. Now we have to make sure that we are aligned with our A/B test allocation and administration system, because depending upon which cell a particular user request has been allocated to, you may get a different model and different experience. This allows us to create different recommendation aspects for each of the various profiles, and eventually we can serve them up once they are in online caches. So this is sort of the high-level general purpose context for all of our pipelines. The models can be different. The languages and the trainer's use can be different, but some of the core basic facts of what you watch and how often you watch, those are the things that are common, which essentially are the various input signals. And then this basic framework allows us to recommend good content. Okay. One of the things that I'd like to talk about that I mentioned earlier on is our key objective metric at this point is optimizing for member joy. And what better moniker for joy than a rainbow? So I'm using the device of a rainbow as a way of essentially talking about what are the various stages in which we are building up this serving. So let me talk a little bit about each of these categories and stages. And so I'll build up this. So you'll see it's cutting off a little bit from the side, but essentially it's the personalization rainbow. The way I've structured this thing up is there's a device layer at the top, which is where you'll get the content, and there's everything below the first violet box is essentially the control plane, runs on AWS, and I've split that up into two parts, in an online and an offline world. And then there's there's a sort of a dichotomy of what is the core function that I'll talk about, and how are the various personalization systems and infrastructure going to sort of help build that up. So we'll start with the first stage here. A lot of what value you can derive out of machine learning is really dependent upon the quality of your data. And so much of our effort and time goes in ensuring that the right training data preparation has happened. And you'll hear me talk throughout this talk about right data abstractions. And so training data preparation is a very important and time intensive and oftentimes compute intensive job too, much not necessarily aligned with some of the things that people talk about, how training and compute resources are the most compute intensive. We do a lot of feature engineering, which is to say that once you have good data quality, you also need to make sure that the right kind of aspects are being used appropriately, so that they can input into your model. Training, of course, is an important element. We'll talk a little bit more about that. And then I talked about data quality in the first stage, and then model quality is just as important. Here, the model quality is really about what are sort of your post-training metrics, and how are you seeing sort of your key objective function reduce, let's say, or improve your precision, your recall, or your normalized mean reciprocal errors. All of that happens essentially in the context of an offline stage, and it does not need to be in the request path. And by the way, offline and online here simply means online is anything that is sort of in the context of member request paths. So you go on a website, you do something, and you get something back. That's all in the member request path. And offline is sort of a batch application that can happen anytime. In the online world, I split this up into a couple of stages. So there's inferencing, which is basically using the trained models and trying to come up with essentially the right score for your business use case. You also need to generate the logs of the data as a way of recording evidence on how that model did and how you're going to be reusing that information later on. And eventually, there's a stage for actually serving it. And I characterize it as an intent to treat. And that verbiage comes from the context of how we are able to go from a traditional batch training approach to more towards the area of reinforcement learning, where we can do contextual bandits and multi-arm bandits based explore-exploit models. And essentially, you provide an intent to treat, and then you treat, and then you record your response. So I'll talk a little bit about that in a brief. But essentially, your last stage is what is the actual treatment that is served to the user. And the distinction between intent to treat and treatment is about there might be caching layer between the device and the online systems, and for some reason there might be business rules. For instance, on an iOS device, you can't show the same video 5 times and things of that nature. And so we want to call a distinction to figure out exactly what impression has been served to the user. And depending upon what impression has been served, what action they took. And we want to learn from those actions, because eventually we'll be making sequence-to-sequence models and trying to figure out sort of a graph of what did we do and what was the incrementality in terms of how we served something. So this is sort of the state of the functions and the categories in which we are operating in. And then I'm sort of going to build up this stack on some of the infrastructure that sort of fits in that space. Okay, so the first thing is we have a fact store. And you can think of this as sort of the repository of useful data recovered from the online world in the backend and the device action world. And so all the facts that you need to compute your features are stored in a fact store. Label generation is an important aspect too. You do a lot of ETLs to try to come up with what is a negative signal and what is a positive signal, because eventually you have to sort of have labeled data, which will be an input into your feature engineering process. And then we talk about 2 libraries here, boson and algocommons. The name don't mean anything to you, but those are the 2 topics that I will actually go and do a much more deeper dive into. But essentially, there are ML libraries that we have written in-house, and depending upon the categories that they span, you can see that there's elements of feature engineering and training and model quality that boson is involved with, and algocommons goes all the way into the online world. And I'll have more to say about that in a little while. Now, a lot of what these libraries provide are essentially frameworks and building blocks. The interface to the data scientists have to be tools that are rich in visualization and exploration, and notebooks provide a very good abstraction to be able to sort of do quick iterative exploration. Even before, when you have sort of a kernel of an idea on what you want to do, you want to be able to sort of quickly code something up, try out an algorithm with some test data, and see whether it has any merit to write up a proper hypothesis that you want to run through a proper A/B test. So notebooks play a very important part and sort of in terms of figuring out what is it that you want to explore. But at the same time, you also want to make sure that once you have identified your key areas, you want to have well-defined orchestrated pipelines that can deploy your production A/B tests and cells. And so a lot of the work that we do and the systems that we have built are in the space of orchestration. Meson is one of the tools that my team built a few years ago. But I won't be getting into the details of either of those topics. As I said, we'll be focusing on just those two for now. Another aspect which is quite important in the model quality space is sort of hyperparameter optimization. Your models have lots of hyperparameters, and one of the tools that we are building right now is trying to figure out how can we have a system that can do accelerate the pace at which you can explore your hyperparameters. And so you need to be able to do it both in sort of an ad hoc explorations phase where you're still in your notebook. In many cases, it's simply a very easy grid search, and you can just do a for loop in your Jupyter notebook, and you can explore parameters and then use those parameters for doing the next round of training. But in other cases, you may be wanting more advanced explorations like Bayes optimization, and if your training can be quite time consuming, then you want to be cautious in terms of picking the right space of finding which set of parameters to explore, and that's when you would need some degree of orchestration, as well as a module that uses hyperparameter optimization. So that's all of this essentially happening still well in your offline state. You still haven't necessarily trained a model, but you have prepared all the data. You have figured out what your features are, and then you're essentially ready to train your model. And then once your models are ready, you are now in the online world. An online world in the sense that these microservices are involved in serving and computing for member request path operations. But before you do that, as I mentioned, that we do a lot of pre-compute, and so we have this pre-compute framework that allows us to sort of take the models coming out of boson and algocommons, and in a batch way, you are essentially able to score and rank and do inferencing there. At that point, once you are evaluating how to do the scoring, you also want to make sure that you have good parameter management systems that can communicate between different microservices. That's another key component which often gets sort of not a lot of focus, but is an important element of how you can ensure robustness and reliability, because now you are in a space where you are responsible for serving, and you're responsible for ensuring that your content can be debugged and troubleshot at the right instance of time. You obviously have to coordinate with the A/B testing platform again to figure out what experiences to serve and not. And eventually, once you have essentially pre-computed your models, and then you need to try to figure out what is the aggregation of all the personalization aspects that you've talked about. And so there's a microservice that is responsible for that. You take out your personalized images and artwork. You figure out what rows that were selected, and you figure out what the rankings of your video ranker are. You all put them together, and essentially you help build up the content for your page. And then there's a tiny layer of API. I've mentioned listed it as tiny. There's a lot of actual magic that happens, but it's not relevant to this talk. But essentially that figures out how to render it for the right device and what do device-specific things, and essentially such. But if you look at this stack, this is much of what you're talking about just before the personalization aggregation is very typical and standard to any ML application. It doesn't have to be a recommender system application. And the way we chose to build some of these tools is interesting, and I'll talk about that when I'll talk about sort of where we came from. But this gives you a sort of a good idea of how we've built something up into a point where we're ready to serve. And finally, we are able to serve a content, which is basically a recommendation. Now, we're not done yet, and we're not done because a very important aspect of closing this loop is around what are the signals that we can acquire at various stages of the stack. At the device level, we want to try to capture what were the interactions that the user was having. From the various microservices level, we want to start logging the various paths that are involved in the personalization, as well as other online services that are involved, like the account service or the viewing history service, which are not part of the core elements of what personalization is doing, but are super important and need to be fed back into the fact store. And so this is essentially the end-to-end scope in which we're operating. So for the rest of this talk, essentially, I will be talking about just these two components, and I'll drill down a little bit more into boson and algocommon, and what are some of our design decisions, and why we chose to build it this way, as well as what are some of the lessons that were learned as part of this exercise. So Netflix is famous for its culture deck. And some of you may have heard the term, I don't know if it's presumptuous for me to assume or not, but there's a bit of a unique culture in Netflix. And one of the things that I really like about it is how the various teams are highly aligned and loosely coupled, which is to say that you don't have a top-down diktat on, you should use this, or there's a strong policy. That same model essentially applies in some of the way we have designed these libraries. These are fairly loosely coupled, but they're highly aligned. They know what they're doing, but they allow for that composability, and it sort of makes it easier for data scientists and researchers to be able to explore using whatever tools they want. But when the time is right for serving, and you care about robustness, you can do it in a way that's reliable, robust, and easy to debug. And so that is sort of an overarching design principle, if you will. But a little bit of a historical context before I get going. As I said, Netflix has been involved in machine learning, especially in the recommendation space, for a really long time. Back in the days when it was inconceivable to have the kind of computing power that we have today and the kind of models that we can train. But as things had grown organically, we had seen that we had a lot of siloed machine learning infrastructure. So there were things that a lot of data scientists were doing based on whatever new academic research was coming out, whatever tool sets that they could use. And there are really not that many opportunities for sharing. And more than that, it's about when one model about, let's say, a video ranker needs to be an input into another model, because we have to do a lot of ensemble-based models. When you're trying to select your rows, guess what is a very important feature in that sort of page ordering model? It's the ranks of the videos. So multiple teams have to interact in the sense that the output of one team's model is a feature in another team's usage. And so lots of incompatibility and dependency issues used to come up, and so we spent a lot of time thinking about how we can come up with the right abstractions, and should we have a clear, well-defined platform. And I think there's strong cases for having that use case, but at least in the specific case for our domain, didn't make a lot of sense. And the reason for that primarily is driven by, and I'll talk about it in more detail, but it's driven by the choice of the serving infrastructure. And the serving infrastructure is all Java-based microservices in Netflix, and we need to be able to run and do inferencing and scoring in essentially a JVM-based environment, and to make sure that we don't have the training and serving skew. You want to have some degree of commonality of code, and so I'll delve into it in a little while. But that was sort of the state before we went forward. And so the key design principles that boson and algocommons are based out of are composability, which is to say that you want to be able to put various pieces together in different ways, in novel ways, and you want to be able to make in such a way that more generic tools can be built on top of that. Ability to share code online and offline is very important, and especially between applications. And the reason for that is because we're at a point where we have gotten many of the big percentage wins in terms of the improvements that some of these ML models can get, and oftentimes what we consider a big gain or a huge win from an A/B test is a 0.2 or 0.05% improvement in a core metric. At that granularity, the value of data errors and bad data becomes super high. And so oftentimes when you don't have alignment between the multiple applications or between an online and offline context, you have all sorts of problems that you can get into. And you don't know sometimes. There's a metric that fails. Was it a problem with the model? Was it a problem with the data? Was it a problem with your idea? And so you want to be able to attack one by other, and so you want to try to minimize opportunities for failures as much as you can. And as I mentioned earlier, avoiding the training and serving skew is very important. It is a result of, I mean, it's often published also, and you hear about it in various talks, how it ends up driving some of your metrics out. And so one of the choices that we made explicitly was we have a mechanism in which we can share both code and data between online and offline worlds. And I'll talk about that, how we do that in the context of the fact store and boson and algocommons in a bit. Okay, so let's get back to our rainbow, or part of the rainbow. And then what I'll do is I'll try to provide some more context in terms of, okay, how are these libraries doing what I was talking about? So I'll start with algocommons, or some part of algocommons first. So algocommons is really just, if you think about it, is a series of abstractions that it defines. It's very generic, high-level stuff. It provides an ability for having define a bunch of data abstractions, data maps and keys I'll talk about. And then it provides some ML constructs. And that's how it enables sort of the feature engineering that is actually done in the boson layer. So if you look at the kind of things you would need, these are the building blocks, and sort of these are the things that application pipelines built on top of them typically do. So they start out with fetching data from the various fact stores, and you need to be able to move data around appropriately. You need to be able to stratify your data sets so that you ensure that the right mix of various attributes exists. For instance, you want some percentage of data from US members and some percentage of data from iPhone users because you're trying to have a generalized model. Boson also defines a feature schema, and I'll have an example for that later in it. You want to be able to get your joins, the label generation has happened and your facts are there, and then you want to put together, join them. You want to transform various features into a pipeline, and eventually you come up with various features. Once you have all of that, and because you have a fact store which is storing online snapshots of data from many days in advance, we are able to enable time travel, which is essentially a funny way of saying that you can go back in time, let's say 3 days or 4 days, and then you can figure out what would have this model predicted and actually what was predicted 4 days ago. And so you really have you have a sort of snapshot in time back, because you can essentially rewind the state of all the microservices that you have facts logged upon, and you can recompute your features, and you can see how this model would have predicted and what it actually predicted. And we're big Back to the Future fans, and so we call that library DeLorean, just to do some time travel. In the training space, algocommons provides really the core abstraction of a model file, which is, it's a JSON-based file format. It's fairly straightforward, and we chose to use our own. There are others like the PMML, but that's just because it's something that worked well. We really needed something simple. There are other abstractions that algocommons provides, but that's sort of the core of what we do. And Boson then provides sort of a high-level training API, and that training API allows you to work, do batch training, whether it's synchronous or asynchronous, whether it's distributed or it's a single Docker across a whole plethora of different trainers. Now, it's important to note that Boson is not a trainer. It is simply the thing that pulls everything together, essentially. And so the core training, and again goes back to this principle of composability. You want to give your data scientists the freedom to explore, and so it allows you to run with various different types of trainers, and I'll have some examples later on about it. And that's sort of the core. Essentially, it provides a clean, simple training API that you can use no matter what kind of training job you have. And for determining model quality, algocommons provides the building blocks for the various metrics. So what are some of the metrics that are going to be used at training time, at scoring time, your standard statistics metrics implementation? We have an open source library for that, which is essentially part of algocommons. Again, when Boson is using some of those metrics, it is able to compute those training metrics, but then it also enables us to sort of run the validation runs post-training. It allows you to create your feature importance visualizations to figure out how good your features are. And then there's the aspect of human in the loop, which I can't emphasize enough. Right? Despite the fact that we want all of these systems to be really automated, we still want to be able to make sure that we have ability for humans to interpret how the training was, and to that extent we take spot checks, but we also are building tools, which I have not listed here, around the interpretability of models, and especially as some of these models are becoming more complex to reason about. Our brains are able to do this job, but we don't know what the hell is going on in our brains, and that's essentially the model interpretability problems. And so this is an active area of focus for us also. But there's still a lot that we can do to tune the model and come up with something that we feel reasonably confident that we can deploy. And finally, Boson doesn't go into the online space, but algocommons does, and algocommons essentially has to do the job of inferencing. And so there's, again, in a production large-scale system, you can imagine this is a framework that's dealing with hundreds of different models for the same use case. And it has to be efficient in terms of how it actually loads the various models. It has to perform scoring. In many cases, well, in most of the cases, I would say, this scoring has reasonable latency requirements because it's running in a pre-compute batch fashion. But as the size of our data increases, the size of our membership increases, those budgets are going down too. So we're on the order of seconds and milliseconds. But even more importantly, there are many use cases where now we're doing online computes, and we have on the order of 100 milliseconds to be able to score something or less. And so being able to write that code super efficiently and be performant is important. That's one of the reasons why we use sort of Java in that space as opposed to a language like Python. You have to compute inferencing metrics, obviously, and then you have to come up with the right prediction. So this gives you a sense of what these two libraries do, and then I will be spending some more time talking a little bit more about each of those. Okay, so algocommons, and much of this stuff I've already talked about, so I'll try to run through some of these ideas. It's mostly just a series of common abstractions. It's really less about machine learning and more about just doing good software engineering and coming up with those right abstractions. It's integrated, as I mentioned, in our Java microservices environment. And very interesting thought. I'm not the lead person on algocommons, but the engineer who wrote it is very opinionated, and rightly so, about algocommons shouldn't use you. You should use algocommons. And so the idea of a library being greater than a framework comes across very, very clearly. So to the extent that how you are able to get value out of it really depends on the kind of abstractions that library exposes. And so the user focus is really key there. Everything is around being able to program to well-defined contracts and interfaces, so the idea of composability. And then there's tremendous amount of modularization, because there's all sorts of jar hell and dependency issues if you just build one big jar. And so you would have literally scores of different sub-libraries within algocommons, so that you're only picking up the right thing that you need for your use case. And so these are sort of just good general software engineering principles, nothing fancy here. And much of what algocommons focus is around the data access abstraction. So let's talk a little bit about those abstractions. Data keys and data maps are two fundamental building blocks. And there's several others, but those are the things that you use to communicate between applications using this library. And within the modeling set, there's component sets, and then feature encoders and predictors and scorers, and last but not the least are metrics. So I'll delve into these a little bit more. So data keys really, this identifies a name to a value. So if there's a viewing history object, this basically says there's a data key that identifies that. And then data map is essentially, it's a map from a data key to the type of data, and including some metadata. I don't know if I will need to get into this, but the high level idea there is in terms of how it's being used. So it's the application's responsibility to figure out how to build up this data map and provide the algocommons, and each of the component knows what data keys it is interested in. And so basically, the application would say, I'm interested in this kind of component. Tell me what kind of data keys you're interested in. You'll get a response back. The application would build up this data map, say, I need viewing history, I need my list data, I need continue watching data, and then you build the right component, and essentially a component is generated for you, and then you can do something with it. So I'm going to run through some of this because it's high-level details. Okay, so the data transform allows you to sort of add, basically, it allows you to figure out how you want to munge your data, essentially. It's essentially a key value mapping for data map. And feature encoders and predictors and scorers are sort of the key abstractions, so I want to talk a little bit about them quickly. So what is the feature encoder? It essentially encodes the value of what the core of your feature is. And so you take in a data map, and then the class essentially essentially encode method right there, it encapsulates how to compute that feature. Feature could be as simple as days on the service, or it could be more complex thing which says that how many times this particular profile has had novel discoveries of new content and stuff like that. And so that logic of that is encapsulated into the feature encoder. You can have feature interactions, and so you can essentially have one set of feature, and you can use transformation that allows you to produce new types of features, and all sorts of inner router products and arithmetic operations can be done. The way the library is written up, you can stack up features. You have an opportunity to automatically dedupe them if you end up reusing those features, and sort of quite handy. So a predictor is sort of the core of the model, which is, and it's in the interface essentially takes a vector of your features, and it is able in a data map, and it is able to implement what the output should be. And so you take in your features and you predict, and that's sort of the essential part of what your model is trying to do. Algocommon supports all sorts of different predictors, standard logistic regressions, and things that are in open source like TensorFlow and XGBoost, but also sort of combinations of those. So weighted added ensembles or feature weighted ensembles, and bandits and sequence to sequence models. And last but not the least, so scorer is. So now you have a predictor, and the scorer sort of provides, okay, what am I going to do with this prediction? So I need to compute a final score. Let's say it's the ranks of one particular video to you, and so that's the abstraction for doing the scoring. Okay, and this is an example of the model language I talked about. Really straightforward JSON abstraction. As you can see, it defines a name, it defines the type of schema in terms of what kind of a model it is, what are the data transforms, what are the various feature encoders, what does the predictor look like. And then another interesting thing is that algocommons provides you various views on the same model. So for instance, this is an example of how the data moves through various data transforms, feature encoders, transformations, and eventually a predictor. And typically the way you're using it is you have sort of this scoring model view, right? You need, here's the data, this is what you normally do. I need to score this, and here's my data. But there are use cases where you want subset views. I only care about this data transformation, or I don't care about prediction, just give me a way to compute the various features. And the way the library is written, it allows you to enable these kind of changes. On metrics, again, some basic building blocks around accumulators, estimators, and then ranking specific metrics like precision recall. We call it a particular rank, precision at recall, all sorts of things. And then regression metrics like root mean squared error. Nothing fancy here, but just something that is necessary for algocommons to do its job. And so now I'll jump quickly into Boson and talk a little bit about the motivation here. So algocommon is sort of those building blocks, and Boson is the library on top and an ML API on top that allows you to use those building blocks. But the key motivation is you want to be able to get the power of your notebook exploration that you want to do in inner loop quickly, but you also want to be able to have a way of quickly deploying that to production and being able to go back and forth between these two. And that was sort of the original motivation where we felt that we need some abstraction layer higher than algocommons, and that was sort of the genesis of building Boson. And that's basically everything I've talked about already, but you can think of it as a subset of Scikit-Learn for the Scala, Java ecosystem. Boson relies quite heavily on the core data frame abstraction of Spark, Apache Spark, and we use it from various stages, and it's really powerful for the earlier stages of data preparation and feature engineering, not so much for training. Data utilities, as you can see, it's a lot of the data preparation work is all about moving data. And you have to often move data between heterogeneous systems. So for instance, you can leverage Spark for doing your feature engineering, but you don't want to restrict yourself to doing training only in Spark. Although we do use Spark ML, or formerly known as MLlib, for training, we also want to be able to use all sorts of different trainers. And so you need to have a good data bridge, and we go and do that through various Docker pathways, and there's a few different ways in which we access data through S3 and HDFS that I don't think we need to get into. The feature schema, here's an example of a feature schema in terms of running. So there's two key parts of it. One is the context, which just says, okay, is it, what is the profile ID, what country, what device, and then the actual items. The items to be trained. So for instance, I want to rank the entire catalog, so the item will be video, or I want to come up with the selection of various rows, and so the item to be ranked there and selected there would be rows. And so again, now this is not this is a text representation of a binary data. This is essentially a nested Parquet format in which we store things. Stratification. So this is a subpart of Boson that we're actually planning to open source. And it's sort of a fairly generalized API using Spark data frames, where you can use native Spark SQL expressions to stratify your input data set. And so let's say you can say, as I mentioned earlier, I want only 8% of US traffic, and I only want no more than 1% of this particular column, where the range or the distribution lies between these two boundaries. And so this is a fairly nifty standalone element of it that we're likely going to send out. Algocommons have the data transformers. This is the feature transformers I talked about. So an example of feature transformation would be you start with sort of tagging certain features, and then you figure out, okay, based on the country and the tenure, I want to stratify. So this person has been a member in this particular country for at least 2 years, and we want profiles of a similar nature. And so you kind of figure out that that's an abstractable sampler, and so you write that separately, and then you can apply that abstraction. And then you want to figure out what is the good definition of what a negative is and what a positive is, because just because I served you some content and you clicked on one, but you didn't click on 1499 or whatever that number is. And so are all of those negative samples? Not necessarily. And so figuring out what those right samples are is also an element. And so those are the kind of things we allow you to sort of build the features together. And so this puts all together how we come up with the various features. So you start with your feature schema or the model. You make sure that in the past that data that you are going to be used has been snapshotted and stored in your fact store. You use your ETL generated label data. You put your labels and features together to essentially have labeled data. Then you use your structured data frame from your fact store using Spark Catalyst for performance reasons. And now you have well-defined structured data, but you still don't have features. And so at that point, you make, as now you're an application talking to algocommons, and you're essentially sending the data maps here, and data maps, feature encoders essentially generate features to you. Once features are there, you merge them with the label data, and eventually you get the structured label features. This is sort of all happening in Boson land, and now you're ready to do your training. And so this DeLorean picture in the middle suggests that not only can you do it for your current features, but you are able to time travel based on what snapshots of data your fact store has. Training, as I mentioned, we need as much flexibility in training as possible, because you want to be able to not restrict your research scientists, and so we support all sorts of various different trainers. The API in Boson itself is really very straightforward and simple. All it says is, here are my parameters for the model, here's my training set, and here's the trainer that I want to use to go train. Now it can be done synchronously when you are running really long training jobs in notebooks and you don't want to sort of hold up your processing, or it can be done in in a synchronous manner. We support tons of different trainers. Netflix has its own internal learning tools library for various proprietary algorithms. Vectorflow is a Netflix trainer for sparse data sets for doing neural networks that we open sourced last year. Obviously, everybody is familiar with TensorFlow and XGBoost and Spark and Scikitlearn are various other trainers that we use. So. Once the training is done, as I mentioned, you want to leverage algocommon's metrics framework and compute the various metrics. Whether it's an MRR or NDCG. You also want to be able to figure out how your models can do custom scoring functions, and algocommons provides sort of that. In Boson, you're able to slice and dice the various metrics, and mostly through SQL Catalyst expressions. We really push hard on Spark in some of those areas. We are able to sort of aggregate, and the reason for that is mostly because of the size of our data, that we have to be as performant as possible, and so we're always on the edge and trying to make sure that we can get the most out of it. So a lot of these are sort of context level metrics, but we also have item level metrics like row popularity. And last but not the least, visualization is important. We have an internal library that we have also open sourced. It's called Vegas, which is basically, think of it like a Scala library for matplotlib. Like Word, it uses the Vega Lite specification format and builds a Scala wrapper around it. It works well with Jupyter and a bunch of other notebooks. We use it for our own internal purposes, but it is open source. Go check it out. And so, what are some of the lessons that we learned as part of this exercise? And one of the first things that comes to my mind is that machine learning is such an iterative process, and it's such a data-intensive process that the focus on making sure that your checks and balances on the data, on the features, on the models, on the trained output, it cannot be overemphasized. And so you want to be able to make things easy to explore, but you also want to keep your productionizing robust. And to be able to go easily between the two oftentimes forces you to make tough choices in terms of, okay, we're going to be doing all our features engineering in a JVM world so that the same code can run in online and offline. Which means that if somebody wants to use Python for their exploration, they have to sort of go through one stage of early exploration, figuring out what they want to do, and when they have a kernel of an idea, they then have to sort of report some of those changes into a JVM world. But we found out that that's worth the price, because eventually the time lost in wrong decisions once they're deployed in production is much worse compared to sort of the effort you have to put up front. And so designing components with this general flexibility is paramount. I also already mentioned about testing, and there's several elements of testing, right? In your typical software engineering, you're done with unit testing, and your integration testing is essentially done. Maybe you're doing some continuous integration, but here you also want to be able to, after your end product is out, your model quality can change depending upon the inputs, because it's not just an algorithm that you're executing. It's really a big part of what your model output is really about the input data. And so having at-scale testing, making sure that you have environments where you are actually training and scoring an environment before you're actually deploying is very important, and all of these have to be essentially metric-driven system validations. If you do that though, doing all of this becomes easier, and it's worth the investment, so that you can sort of give the joy that your customers get ultimately watching a Netflix show. That's pretty much it. Questions?
Okay.
Yes.
So you mentioned that you're storing your feature as a nested JSON. So I was wondering what that decision.
We're not showing the features as a JSON. That's just a feature schema. And if you pay close attention to it, those are sort of dotted lines. Essentially, the features, as I mentioned to you earlier, we actually store the facts and